This is Mr. Picard with another geometry video. Today we're talking about the areas of regular polygons. We will look at the formula that's needed in order to calculate those areas. It can be a little bit complex. There's a lot of pieces of our study of geometry that need to be brought together, and so please pay attention and watch carefully. We need to cover a little bit of vocabulary. A couple concepts we'll introduce, a couple words we'll introduce in this section. First of all, let's remember that it is possible to circumscribe a circle about any regular polygon. So whether I'm talking about a regular or an equilateral triangle or a square or a regular hexagon, regular pentagon, any regular polygon, I can circumscribe or draw around a circle so that the circle includes each of the vertices of the regular polygon. And so you can see an example of that here. Center of the regular polygon, that's a new word for us, not in the sense that we've never heard the word center, but in the sense that we're defining it a different way here. The center of a regular polygon is the center of the circumscribed circle. So if I talk about the center of this hexagon, well, it's the same center as the circle that's drawn around it. Note also that when we talk about the center of a regular polygon, it is the midpoint of the diagonals that go from opposite vertices. So you'll find that these diagonals are all concurrent in this point, and that point is called the center. Next we have a radius. We're familiar with the word radius, but we've talked about the word radius in the context of circles. Notice in this circle, this is called a radius here. And in fact, it's also called the radius of the corresponding polygon. When we talk about this hexagon and we talk about the radius of the hexagon, the radius is the distance from the center of the hexagon to one of the vertices. You'll notice, unlike in a circle, where there are an infinite number of radii, in this hexagon there are exactly 6 radii. And of course, if you're dealing with any polygon with n sides, there are exactly n radii. So in a regular octagon there are 8 radii, in a regular pentagon there are 5 radii, and the list goes on. This word is definitely new to us, this word apothem. It is the perpendicular segment from a side to the center of the polygon. So in this case, the apothem is here, this red segment here. Notice that the apothem is shorter than the radius. It will always be shorter than the radius because the apothem always goes to the segment here, not to the vertex, but to the segment. Also notice that if you take the apothem and one of the radii, and then half of this side of the polygon, you'll always form a right triangle every single time. Now let's talk about finding angle measures in regular polygons. The process is pretty much the same no matter what kind of a polygon you have, although in some polygons there are shortcuts. Here's a regular pentagon. There are 3 angles numbered in here. You can see this is angle 1, which is a central angle. Angle 2 is formed by the apothem and the radius, so it's half the central angle. And angle 3 is this angle in here. How do we actually find the measure of each numbered angle? Let's deal with number 1 first. The measure of angle 1 is pretty simple, actually. You can see that the measure of angle 1 is repeated 5 times around because this is a pentagon. So therefore, the measure of angle 1 is equal to 360 divided by 5. And that is equal to 72 degrees. Next, let's take a look at number 2. Because angle 2 is formed by this altitude in the triangle, or the apothem as we call it, the measure of angle 2 is equal to half the measure of angle 1, and so therefore it's 36 degrees. And then finally, to find the measure of angle 3, we'll use the triangle angle sum theorem. We know this is 90. We know this here is 36. So we know that the measure of angle 3 plus 36 plus 90 is equal to 180. To say that another way, we know that the measures of angle 2 and 3 are actually complementary. In other words, the measure of angle 3 plus 36 equals 90. You can see that here. And so finally, we just subtract 36 from 90, and we end up with 54 degrees. So we can pretty easily find these measures. Again, looking at that, to find the measure of a central angle, simply take 360 and divide by n, where n is the number of sides. To find the measure of the angle formed by a radii and an apothem, we divide that number by 2, the central angle by 2. And then to find this, we just use the triangle angle sum theorem. Let's give it a try again. Let's find the measures of each angle in a regular octagon. Here is the regular octagon. The first thing we need to do is actually draw in the center, and then go ahead and draw in 2 consecutive radii. Finally, let's go ahead and draw in a third radius, just so we can find the measure of angle 1. We'll draw in an apothem, and find the measure of angle 2, and then the measure of angle 3. So to find the measure of angle 1, we divide 360 by 8, and that is equal to 45 degrees. To find the measure of angle 2, we divide the central angle by 2, so that's 22.5 degrees. And to find the measure of angle 3, we know that the triangle angle sum theorem will work on that triangle, so we take 90 minus 22.5, and we end up with 67.5 degrees. You should work through several examples of that so you can find those angles very easily. They should come to you fairly quickly. The next thing we need to do is derive a formula for the area of a regular polygon. I'll do this 2 different ways. First way we'll do it is to recognize that if you have a regular n-gon, that is a polygon with n sides, and each side has s as a side length, the radii of the polygon divide it into n congruent isosceles triangles. So if we're talking about a square that we know has 4 sides, then the radii divide it into 4 congruent isosceles triangles. If it's a triangle, 3 sides, the radii divide it into 3 triangles. If it's a pentagon with 5 sides, we know that the radii divide it into 5 triangles, and so forth and so on to infinity. That's important to keep in mind. Each triangle has an area equal to 1/2 AS. Notice A here is the apothem. It's also the height of the triangle. That's important to remember as well. So the area of that triangle, which is 1/2 base times height, area equals 1/2 base times height. We can see here the base of this triangle is actually S, and the height of the triangle is actually the apothem of the polygon. And so we find that the area of that triangle is 1/2 times the apothem times the side of the polygon. Next, since we have n congruent triangles, so in an octagon, for instance, there are 8 of these. N congruent triangles, the area of the n-gon must be n, the number of triangles, times 1/2 times apothem times side. All we're doing is taking into account each of those triangles. The perimeter of the polygon is always equal to n, the number of sides, times s, the length of each one of those sides. So p equals ns. Finally, we can substitute p in the second formula for ns in the first formula. Let's just take a look at that. We have this area equals n times 1/2 as. That means area is equal to ns. I'm just going to bring this s out of the parentheses by the commutative property multiplication. Ns times 1/2 a, where this is the number of sides, the length of each side, and this is the apothem. And so when I rearrange this thing, I can take this p, and since p is equal to ns, I'll substitute it into this, so that becomes a p. And so I find that a is equal to 1/2 AP. A is equal to 1/2 AP, where it's the area of a regular polygon, and it's equal to 1/2 times the apothem times the perimeter. Let's look at that from one other perspective. I have an animation here. You can see this is a regular octagon, but I could have done this with any shape. Could have been a hexagon or a pentagon or even a square. And what we're going to do is we're going to notice that anytime we have a regular polygon, it can be divided into n number of congruent isosceles triangles. And in this case, the octagon is divided into 8 isosceles triangles. Notice the perimeter is measured around the polygon, and that's each of these sides would be taken into account. And notice the apothem is also labeled in here. It's the height of one of these triangles. Now, as we open this thing up, we're going to unpeel it like we would an orange with the segments in place. We'll find it would look like this. You can see that the P, which was the perimeter, is now actually the base along here, along these triangles. The apothem is still in place, and so we have the same exact area. It's just arranged slightly differently. The next thing we're going to do is fold all the peaks. So what we did is we cut half the peak off of each one of these triangles, and we'll fold them right down into those valleys. And as we do that, you can see it changes shape. With those peaks folded, you can see we've actually formed a parallelogram. Notice that P, which was the perimeter of the original octagon, is still here, except now it's this value is the base of the parallelogram. The height of the parallelogram in here, you'll notice, is exactly 1/2 the apothem. And so we find those values presented here. 1/2 AP is actually 1/2 of the apothem, which is the height of the parallelogram. P is the perimeter of the original octagon. And so we find that the formula for the area of a parallelogram can be related to the area of a regular polygon. We know that a parallelogram has area base times height, and in this case, the base is the perimeter of the octagon, and the height is 1/2 of the apothem. And so we've derived that formula in a slightly different way, but we get the same exact answer. Let's just look at that a couple more times. There's the regular octagon, and it becomes a parallelogram. And so we derive the formula. We can state that as a theorem, the area of a regular polygon is half the product of the apothem and the perimeter. Again, A equals 1/2 AP. Keep in mind that that perimeter is equal to NS, that is the number of sides times the length of one side. Here's a quick review problem. It says find the area of a regular decagon, that's 10 sides, with 12.3 inch apothem and 8 inch sides. So the sides are 8 inches, which means the perimeter is 10 times 8. Let's just write that down. Perimeter equals NS. Perimeter equals 10 because there are 10 sides, times the length of each side. So the perimeter is 80 inches. We know that the formula for the area of a regular polygon is equal to 1/2 AP, where A is the apothem and P is the perimeter. Therefore, the area of this decagon is 1/2 times the apothem, which is 12.3. And that is being multiplied by 80 inches, which is the perimeter. We can take this 1/2 and multiply by 80. We end up with A equals 40 times 12.3 inches squared. And finally, I believe that's 480 plus 12, 492 inches squared. Let's just check that on a calculator. 40 times 12.3, 492. So that's good. We have one more problem here. It says find the area of a regular pentagon with 11.6 centimeter sides and an 8 centimeter apothem. At this point, let me just note that oftentimes finding these values can be the challenge. In these example problems, I'm giving you apothem, I'm giving you the value of the perimeter or at least a side. But in other problems, you'll need to calculate the perimeter, you'll need to calculate a side, you might need to calculate an apothem. Those values are almost always calculated using right triangle trigonometry. So please be aware of the fact that trigonometry is very much alive and well, and it's something that we need to constantly be reviewing. For this problem, we just put it into the formula. The area of a regular polygon is equal to 1/2 times the apothem times the perimeter. Notice that we have a big A and a small a here. Please be careful about that, because the big A is area and the small a is apothem. If you haven't gotten in the habit of distinguishing between small and large letters when you do mathematics, now would be a really good time to do it. So in this case, we have area is equal to 1/2 times the apothem, which is 8 centimeters, times the perimeter. Now, we weren't given perimeter, we were given the side as 11.6, but we know that the perimeter of an n-gon is always equal to ns. So in this case, there are 5 sides, it's a pentagon, and each side is 11.6 centimeters. So we can multiply the half times the 8, which is 4 centimeters, and then we need to multiply 5 by 11.6. That seems to be 55 plus 358, I believe, centimeters. Let's check that on a calculator. That's 5 times 11.6. 58 is the answer. Then we need to multiply that by 4 to get our final answer. 232. Our area is 232 centimeters squared. And that's how we find the answer. All right. From this lesson, we had a couple of vocabulary words, and we walked away with a single formula, A equals 1/2 AP. Remember again, big A is area, little a is apothem, P is perimeter. I strongly recommend you work through a few problems on your own. And as always, if you have any questions, feel free to send me an email.